So, in this lecture we will discuss about the update rules for the parameters in convolution neural networks. So, this lecture we will discuss about the update rules for the parameters in convolution neural network, which I call it as CNN. Also we have seen in the course that Professor Shayan has discussed the ideas of multilayer perceptron in detail, starting from the ideas till the derivation of update rules for the parameters in multilayer perceptron. And we see that multilayer perceptron, which I call it as MLP, forms the backbone network for convolution neural network. However, there are important differences between multilayer perceptron and CNN. So, what we will do is we will briefly visit the multilayer perceptron and then we will get into the details of the derivation of update rule for the parameters of CNN. Okay. So, multi-layer perceptron So, in multi-layer perceptron we have input layer, we have hidden layer and output layer. So, let us assume that we have input from a d-dimensional space and we have capital M number of hidden neurons and we have k output neurons, and this network multi-layer perceptron is a fully connected network, in the sense every neuron is connected with every other neuron. So, this algorithm or multi-layer perceptron network has two steps. First step is the forward pass. So, in this step what we do is, for every input we compute the output using the existing parameters, and those parameters are nothing but the weights connecting ith and the jth neuron in the layer L, that is Wij of L. So, using these parameters we compute the output in the forward pass. The actual learning happens in the second step, which is the backward pass. So, now we will look at the backward pass. So, what the actual learning happens in this step and this requires the computation of local gradients at each layer. So, this is the this is the idea behind multi-layer perceptron. So, since we have said this forms the backbone of CNN, we will look at the similarities between the MLP and the CNN. So, let us look at the architecture of CNN first. So, now if you look at the architecture of CNN, we have at the input side, let us say an image of size 3 cross 3. In general, it could be an image of size n by n. So, here as an example I have considered 3 by 3 image. Let the pixel value of this image be x11, x12, x13 and so on. Now, this is the input. We have a filter of size say 2 by 2 and in general it can be of size k by k, which is less than n by n, and let the parameters of this filter be W11, W12, W21, W22. Now, what happens in the convolution neural network is that this filter will be first rotated by 180 degree. So, by that what I mean is the following. So, you just consider this filter and you exchange these two elements and similarly these two elements. So, we get W22, W11, W21, W12. Now, this is rotation by 180 degree and we slide this mask or filter over the image starting from top left corner to bottom right corner. So, we slide this mask or kernel, or we call that as filter, over the input image starting from top left corner to the bottom right corner. That is, we have the input image like this x11. I am repeating the same here. I will place the mask at the top right left corner and the parameter values are this is the rotated mask. So, I have W22, W21, W12, W11. So, the operation that I perform is as follows. I define a term called H11 which is given by X11 W22 plus X12 W21, X21 W12 and X22 W11. Similarly, the filter will be moved to the next location. Now, I define another term called H12 which is given by X12 W22, X13 W21, X22 W12, X23 W11, and similarly when the filter is placed here, I get H21 as X21 W22, X22 W21, X31 W12, X32 W11, and finally I get H22 as X22 W22, X23 W21, X32 W12, X33 W11. So, because of these operation I get these 4 different values. I am calling them as H12, H11, H12, H21, H22. Now, the next step in the convolution neural network architecture would be to apply activation functions phi on these values. Typically, the activation function is ReLU function, and then one can use pooling. Now, this forms one block in the convolution neural network, and this block will be repeated many times depending on the application or depending on the computational resources available. Therefore, what we are doing here is we will consider only one block and will derive the update rules for the filter or the kernel or the mask. Now, let us look at the difference between MLP and CNN. So, first we will look at MLP. So, as I discussed before, we have set of inputs, set of hidden neurons and output neurons. Now, this network is a fully connected network. However, when we look at the convolution neural network architecture, we will see that there are important differences, and that is in CNN the network is partially connected, and the another important difference is that the concept of weight sharing. Now, in CNN we will see the differences when compared to the MLP architecture. Now, we will understand these differences with an example. So, for that let us go back to the set of equations that I wrote here. We have 4 different terms H11 up to H22. Using these equations we will understand the differences. So, for that, we will see the CNN here. So, I have inputs x11, x12, x13, x21, x22, x23, x31, x32, x33. Now, I defined 4 different parameters which are h11 up to h22. So, I have h11, h12, h21, h22. Now, let us draw the connections by looking at this set of equations. So, in order to get h11, we need x11 weighed by the parameter W22. Okay. Similarly, in order to compute h11, we need x12 weighed by the parameter W21, and we need x21 weighed by the parameter W12, and finally we need x22 weighed by W11. So, these are the connections that we can write from the input layer to the next layer weighed by different parameters. Now, let us look at how one can obtain h12. So, if you go back and see the equation for h12, we need x12, x13, x22, x23. So, we need x12, that is here, weighed by the weight W22. Therefore, we have connection from x12 to h12 weighed by the parameter W22. So, if you observe the connection between x11 and h11 and the connection from x12 to h12, we see that the same parameter is being used. So, this is the idea of weight sharing. So, similarly, let us proceed with the other connections. So, we need x13 weighed by W21. We need x13 weighed by W21, and we need x22 weighed by W12. And finally, we need x23 weighed by W11. So, similarly, I can write other connections so x21 weighed by W22, x22 W21, x31 weighed by W12, x32 and x32 with W11. And finally, to get H22, we need x22 with W22, x23 with W21, x32 and we have one more actually, it is x33 . So, this completes the connection between input and the next layer in CNN. So, now one can apply activation functions for these values. Another important observation that one can make here is that it is not a fully connected network. So, this is not a fully connected network. So, now, during forward pass, so we have an input, we compute these Hij's and we apply activation functions and then we perform pooling and this is continued. So, now let us understand in the backward pass how can we update these weight parameters. So, for that we need, if you go back and see the multi-layer perceptron, we need to compute the local gradients at each layer. So, now let us assume that we have local gradients in this layer. Now, let delta 1 1 be the local gradient at this node, delta 1 2, delta 2 1 and delta 2 2. Now, we need to compute the local gradients at these nodes. So, let us see how it is computed. So, at this point at the node x11, the local gradient would be computed as follows. So, we have to take local gradient from the previous layer, weight by the parameter connecting this node x11 node and h11 node. So, therefore, we write delta 11 weight by W22. Similarly, if I want to calculate the local gradient for the node x12, we have to look at all those connections from the previous layer to the node x12. So, we have connection from h11 and h12. So, therefore, we write W21 delta 11 plus W22 delta 12. Similarly, for the node x13, we can write delta 12 W21. So, like this one can compute the local gradients at this layer. So, this can also be computed as follows. Okay, we have the filter which is rotated by 180 degree like this, and we have set of local gradients delta 11, delta 12, delta 21 and delta 22. Now, what we do is we perform convolution between this and this. So, what happens is the following: during convolution, so this mask will be rotated by 180 degree and that will give us W11, W22, W12, W21, and then this mask will be moved over this set of local gradients starting from top left to the bottom right. We will see that in a minute. So, initially the filter will be placed like this. So, this will give us delta 11, W22. Next, the filter will be moved to the right. So, we have W21, W22, W11, W12. Now, this gives us W21 delta 11 plus W22 delta 12. Then, so similarly one can move the filter here and can get W12 sorry delta 12 W21. So, now finally one can get all the values at each node, which is given by W11, So, in this way one can get all the local gradients at the input layer. So, here we saw that we are looking at the rotation of this the filter. So, this was intuitive way of getting all the local gradients at the input layer involving the rotation operator on this kernel or the mask. Now, we will see through mathematics how this is carried out. So, in the standard MLP, the local gradient of neuron J in the L layer is given by delta J of L as dou E by dou Vj of L, where E is the error and Vj of L is summation over all possible k w j k L phi v j L minus 1 phi k at the L minus 1th layer plus the bias at the Lth layer. Okay. We see that in MLP we have used the dot product between the weights and the activation function. However, in CNN this is replaced by convolution operator. Now, with this we define the local gradient as delta x comma y at layer L, where x comma y indicates the location of the mask on the image, as dou E by dou V x comma y in the Lth layer, where V x comma y L is given by summation over all possible a comma b at L E of L minus 1 x minus a y minus b plus b x comma y at the Lth layer. So, further simplification yields delta x comma y L given by two summations over all possible x prime over y and y prime dou E by dou V x prime y prime at the L plus 1th layer So, what this equation really means is that we have to look at all the local gradients from the previous layer connected to the node x comma y, okay, and that is the reason we are using the chain rule and summing over all possible x prime y prime from the previous layer. So, let us simplify this further. So, this is nothing but delta x prime y prime at the L plus 1th layer. So, therefore, let us substitute for V of x prime y prime at L plus 1 layer. Now, let us define x prime minus a as x and y prime minus b as y. So, if you look at this term, the derivative is non-zero the derivative of phi with respect to v x comma y at the nth layer is non-zero only when x prime minus a is equal to x and y prime minus b equal to y, and all the other terms will behave as a constant, and hence the derivative will be 0 with respect to v. And also you can see here this, the bias term is independent of x comma y, and hence this term will go to 0. So, with these conditions we can write x prime y prime delta x prime y prime at L plus 1th layer as w a comma b at L plus 1th layer and phi prime v x comma y at the nth layer. Also, we know that x prime minus a is equal to x implies a is equal to x prime minus x, and similarly y prime minus b is equal to y, and we get b as y prime minus y. Now, if you substitute for a and b here, we get this is nothing but the local gradient at the nth layer for the node x comma for the location x comma y, and this can be compactly written as a convolution between the local gradient at L plus 1th layer with w minus x minus y L plus 1 layer where w minus x minus y at L plus 1th layer is obtained by applying that 180-degree rotation operator on w x comma y at L plus 1 layer. So, now what we have seen is the computation of local gradient at the nth layer, but what we really want is the gradient with respect to the parameters. So, we will see that now. So, we want dou E by dou A comma B at nth layer. So, this is given by summation over all possible x comma y, which is basically looking at all the nodes connected to the node a comma b from the previous layer. So, this term is again delta x comma y at nth layer, and let us substitute for v of x comma y at nth layer as before. Again, if you look at this term, the derivative term is non-zero only when a prime is equal to a and b prime is equal to b. That is for this term. However, if you look at the bias term, which is independent of a comma b, and hence this term goes to 0. Therefore, we can write so this happens only when a prime is equal to a and b prime is equal to b. This can be compactly written as convolution between the local gradient at the Lth layer and the activation function at the L minus 1th layer. Where phi of v minus a comma minus b at L minus 1th layer is given by phi of rotate 180 degree operator operating on v of a comma b L minus 1, the L minus 1th layer. So now we have the gradient of error with respect to the weight parameter, and one can use this information to update the weight parameters. Now let us summarize the update rule procedure for the parameters of CNN. So the first step is, for every input we compute the output of each layer as v of x comma y at Lth layer is convolution of the weight parameters with the activation functions from the previous layer plus the bias term at the L layer. Second step is to compute the error E at the output. Third step is the actual backward pass, where the actual learning happens. So during the backward pass we compute the local gradient delta x y at the Lth layer as convolution of local gradients from the L plus 1th layer with 180 degree rotated weight parameters or the mask from the L plus 1th layer, along with the activation derivative of the activation function at the Lth layer. And finally, we can use the gradient of error with respect to the weight parameters, which is given by convolution between the phi of rotate 180 degree operator operating on V of a comma b at L minus 1 layer. So, these 4 steps will provide the procedure required to update the weight parameters in the convolution neural network. Thank you.